And let's go and get the share set up for the textbook. And let me move the taskbar out of the way so I can read the textbook. Okay, it'll scoot down here as far as it will. Okay, and now I think I need to move the two of you up as far as I can so I can read the textbook. Okay. All right, any questions, issues, concerns, problems? All right. If not, I can't think of any reason not to go on and get started. I wish the others were here, but hopefully they'll be coming in fairly soon. We're in Chapter 2, Chapter 2, First Order Differential Equations. We're in 2.1, Solution Curves Without a Solution. Sort of sounds like a oxymoron or something like that, but it's makes sort of sense in this context. And we're on page 43, near the top of the page, but not right at the top. We finished that right at the end of class last time. We're beginning today with autonomous, and that's what we've been talking about in section 2.2. 2.1.2. Let me make sure I said that right. Yeah, 2.1.2. We've been talking about autonomous differential equations. Okay, now we're going to tie together two things we've done. Way back in chapter 1, we talked about direction fields, and we sort of let them slide for a while. Okay, and then we were talking about autonomous differential equations. Remember, autonomous differential equations have no x dependency. Well, wait, the differential equation does, but the right-hand side does not. The y has x dependency, but the derivative does not. Okay, this thing right here, dy dx, is only a function of y. So you see all across for all values of x's, all the y values are the same. So what we're doing is melding these two concepts, the direction fields and what we know about autonomous differential equations. This is one where your y is equal to 1 is your critical value. Now remember, critical value here is somewhat similar to what it was in Cal 1 when we were doing critical values of functions, but those were with regard to x. What made the function equal 0, what x value said. Now we're doing them with what y values make that 0. And here is an example. The figure distributes the direction field for an autonomous differential equation. dy dx is equal to 2 times y minus 1. Okay? Now, first order differential equation, what makes that derivative 0, meaning the slope of the tangent is 0, is when anytime y is equal to 1. And you see the little red arrows here. There's y is equal to 1. All those derivatives are equal to 0 there. Okay? Then as you go up a little bit or down a little bit, if you go up a little bit, y is greater than 1, so 2 minus y minus 1 is positive. 2 is positive, so you've got slightly upward bending slopes. That 2 makes them bend up a little more rapidly than they would otherwise. Oh, here comes Jesus, if I can get him in. Actually, I'm in the way. I can't get him in. There we go. All right, now I've let him in. See, that's the thing. So many things open at once. It makes it hard to see when people are coming in, and it also makes it hard to get them in. And here's Jesus. All right. So 3 out of 5, that's better than 50%, but still not as good as I'd like to see. Y'all have been perfect attendance for a while. Okay. Let me make sure nobody else is out there waiting that I can't see. Hold on just a minute. Nope, just the three of you. Okay. Now, Jesus, we're on page 43, chapter 2, first order differential equation, section 2.1, specifically section 2.1.2, autonomous differential equations, and we're looking at autonomous differential equations and direction fields, these two concepts that we sort of tied together, or that's what we're doing here. So this is the equation we're looking at. dy dx is equal to 2 times y minus 1. We just noted when y is equal to 1, that's where you have your critical value. That's where the slope of your derivative is always equal to 0. Notice this isn't with respect to x. The slope depends only on the y. Okay? Now, we're just saying that when y was greater than 1, these are all positive slopes, and when y is less than 1, that makes the slopes negative, because y minus 1, if y is less than 1, will be a negative number multiplied by 2, so that makes them all negative. So below y is equal to 1, all these slopes are downward. Now, what they are saying here, which we've already sort of said, the slopes of the linear elements in a horizontal line are all the same because there's no x dependence on the slopes. Okay? On the y, there is dependence on the y. Here it's 0, there it's slightly positive, more positive, almost going straight up. Slightly negative, more negative, going down. Okay, till it goes almost vertically downward. Okay, so that's an example. Now, referring to what we were saying before, remember at the bottom of the previous page we talked about attractors and repellers. These are both being repelled and moving away. So this is basically an unstable situation. The larger the number of x, the more and more further and further apart you are going. Okay? Just trying to tie several of those concepts together. All right, any questions on that? Let's move on down to what they call translation property, which is sort of related to stuff you did in even pre-calculus algebra. You may recall from pre-calculus mathematics that the graph of a function y is equal to f of x minus k is translated to the right k units, where k is a constant. I'm assuming k is a positive constant. Okay, if k is a negative constant, then you just translate it to the left. Okay, the graph of y is equal to f of x is rigidly translated or shifted horizontally along the x-axis by the amount absolute value of k. Okay, and whether k was positive or negative, it shifted that amount. It's shifted to the right if k is positive, to the left if k is negative. Turns out that under conditions stipulated for equation 2, which we did last time, solution curves for the autonomous first order differential equation are related by the concept of translation. To see this, okay, so here's the function we have. dy dx is equal to y times 3 minus y. Okay, first thing I would note here, y is equal to 0 is a critical value. And sure enough, all the slopes are 0 there. Okay, y equal 3 is a critical value, and all the slopes are 0 there. Okay, now, if y is less than 0, so y is negative, so this will be negative, and if y is negative here, 3 minus a minus number is 3 plus a number. This part would be positive, but y being negative, that means everything less than 0 is going to be negative. Okay, and sure enough, all these slopes are heading downhill here. Okay, now if y is in between 0 and 3, y is positive because it's greater than 0, and if it's less than 3, then this term is positive, so all your slopes are positive here, okay? And for y greater than 3, y is positive, but 3 minus y would then be negative. So all these are negative slopes. So you see your direction fields are indicating. Now, of course, where here the slopes are 0, so near that, they're going to be slightly positive down here, slightly negative up here. Slightly positive here, slightly negative here. And the further you get away, the more they bend down. So y is equal to 3 is an attractor up here, to use that earlier term. It's a repeller at y is equal to 0, okay, for what that's worth. Now, what they're talking about now, though, is you can add rather than plus 3, do some other number, okay? Well, that wouldn't quite be right. Let's see. And by the way, I was calling those your critical values. I also called the equilibrium solutions. Remember, equilibrium for small x's, negative x's, y is equal to 0 is your equilibrium solution. For large x's, y is equal to 3 is your equilibrium solution. Okay. So let's see this red statement here. If y of x is a solution of an autonomous differential equation, such as that, okay, then y1, which is y times x minus k, yeah, y of x, okay, that's not a times. I was going to say that makes no sense. Y of x minus k is also a solution, okay? So here your solution curves would be here. Now, if you didn't have a initial value, you don't know which curve you're on, so here's your family of curves. The blue curves in between these two, red curves in between, above y is equal to 3, the green curves down here. And notice they're all parallel to each other. That's what it's trying to illustrate. Now, if you have an initial condition, such as you do down here, y of 0 is equal to y0, then that picks where you are. That picks which one of these curves you're on. So if y of x equal e to the x, okay, all right, for all real numbers x is a solution for an initial value problem, that's dy dx is equal to y. That certainly makes sense because d of e of x is e of x, so that sure makes sense there. Y is equal to 1 is a solution. Then you know that this is your boundary condition or initial condition. So the solution would be okay. All right. They're different initial conditions. Let me scope down here. Whoa, they don't show that, do they? Okay. Basically what they're saying is these are not the curves for this one, okay? But it would just be a translation one side or another depending on your initial condition. Initial condition y of 0 equal 1, that's going through the point 0, 1, okay, which is where most of your exponential functions will go through. If you have that y of 0 is equal to, or y of 5 is equal to 1, that means you come over here to y is equal to 5, that would equal the 1 value, so that would be a curve. Your exponential curve would go through 5, 1, but be exactly parallel to the one that went through 0, 1. That's all they're saying. And this would be basically your solution then. So it's just sort of general things. This section or subsection here doesn't have any remarks, yay. So let's move on to your homework exercises here. I've assigned most of these before. And 2.1.1 direction fields, do either 1 or 3. They should both be in the back of the book. Okay, the odds are back there. Then do either any of the odds 5 through 11. They should be in the back. If they're not, don't worry with them, but find some that are. It's 5 through 11. Then do 13. That should be in the back of the book. The answer should be there. 15 or 7. No, 15. Okay. That should be in the back of the book. Okay. Don't worry about the discussion problems. Okay. But beginning with 2.1.2, these should be in the back. 19 should be back there, and any of the odds 21 through 27 should be back there. 29 should be back there, which is this one right here. Whoops. Did someone else come in? I don't think so. No, just got the 3 of you. Okay. So 29 should be in the back of the book, and that's where you stop. Usually, now if you find any of the discussion problems that do have answers in the back, certainly look at those. You might find those helpful, useful. Mathematical models, again, you can look at those if you'd like to. Those are the ones we talked about in 1.3. Most of these are, so you can certainly look at those. So that finishes 2.1, finally. Okay, and we're going to start 2.2. This far along in the course before we ever solve a differential equation. I don't like the way this book is put together, but this is how they're put together. And a lot of books do this now. They do all this sort of esoteric stuff that give you an idea of what's going on, supposedly. But in reality, I just assume, how do you do this stuff, okay? So everything we've done up till now has been talking about, verify this is true. You know, now we're going to finally solve some differential equations. The easiest ones to solve are these separable equations. Okay, so we begin our study of solution methods with the simplest of all differential equations, first order equations with variables that you're able to separate one from another. Okay, and when we say that, we mean in a multiplication or division sense. Because the method discussed in this section and many other methods involving solving differential equations involve integration, you're urged to refresh your memory on the important formulas in integration, like integration by parts, those kinds of things. So here is a situation. Consider the first order differential equation, dy dx is equal to f of xy. Now when they phrase it this way, you have no idea what the relationship between x and y are on the right hand side. When f does not depend on the variable y, this is reverse of what it was before, that is only depending on x, like f of xy is now g of x, there's no y dependence. Remember in autonomous, it was only y dependence with no x dependence. Now it's the reverse of that. That's equal to some g of x. That can just be solved by integration. And back when you were doing integration, they like to throw in doing differential equations when you're doing just this simple kind like this. So if if g is a continuous function, okay, then integrating both sides gives this. Now here's what I like to do first. Think of writing this as a differential. This is as a derivative. It's a differential equation, sure, but it's written as a derivative. dy dx is equal to g of x. If you wrote that as a differential, that would be dy is equal to g of x dx. It's kind of like you're multiplying both sides of the equation by dx. Of course, dy dx is not a product, it's an operator. but you still treat it as if it's the same because that operator came from taking a difference quotient. You remember that? So you can sort of do that, okay? Now, so if g of x is a continuous function, we hope to be able to integrate it. So write this as dy is equal to g of x dx. Integrate both sides. The integral of dy by fundamental theorem of calculus is just y. And then whatever the integral of g of x dx is, and if it's a continuous function, we hope to be able to integrate it. That's going to give you some capital G of x, the antiderivative of g of x, plus some constant c, where that g of x is your antiderivative for an indefinite integral of g of x. So what if this was what your case was? Dy dx is equal to 1. Let's do this on the whiteboard. I see no reason just blah blah blahing what they do. Let's actually do it ourselves. Now, I got to move some things around. Ryan, you're in the way. I'm going to move you over here. Got to move this taskbar as much out of the way as possible. And I'm going to move the whiteboard as far to the left and up as possible, so I get maximum white space to work with. Okay. Now, I was going in the book and not turning the, in the PDF book. I wasn't turning the pages in mine. So here is, whoa, here comes James. All right, good deal. Hold on a minute. Let me get James marked presence. Okay. All right, we're only missing Jemanuel, and he just showed up too. So he must have been following James. Okay. Perfect attendance again today. Way to go, team. Love to see it. Okay. In fact, this class, I'm pretty sure, is one of the highest percentage attendance I think I've ever had. Way to go. Keep it up. Okay. Now, for James and Jemanuel, you just got here. We're in Chapter 2, First Order Differential Equations. We finally finished 2.1 or 2.1.2. Finished that. I gave you your homework assignments there. We're starting in 2.2, Separable Equations. And we're doing, it's not exactly an example. It's just one they say, well, they say for example, but it's not one done in the book. So here we have dy dx is equal to 1 plus e to the 2x. Okay. Now, they just tell you the answer. I don't think that's very fair of them. Let's do what I just said. Let's write that first in differential form. If I could get the pen to show up somewhere here. There it is. Okay. So that's writing it as dy is equal to 1 plus e to the 2x. This pen just will not write well. Dx. Okay, I can't write. Okay, we're going to integrate both sides of this. I may actually put this in parentheses so it'll be easier to see. Now, integrate a derivative, a perfect derivative. Fundamental theorem of calculus says that gives you y. And y is a function of x. Okay, equal. Now, antiderivative of 1. Please, someone, tell me what that is. X, right? Okay. Antiderivative of e to the 2x. Okay. Now, if you need to, go up and do your u substitution. Let u, if I could get my pen to write, let u equal 2x. Then du is equal to 2 dx. we don't have a 2dx, we have a dx, so let's divide both sides by 2. Okay, and these will go out, and then what we have, I've done the first integral, let me do the second one here, plus the integral of e to the u, or let me do the 1/2, take that 1/2 on the outside of the integral, e to the u du, because du over 2 was dx. Okay, well, hopefully you can do that one. That's x plus 1/2 of, what's the antiderivative of e to the u? E to the u, just like the derivative of e to the u is e to the u, antiderivative is e to the u. Okay, but what is u? 2x, so that would be e to the 2x. Okay, plus c, indefinite integral, you need that. All right, now I'm not quite sure that's how theirs looks. Oh, that is exactly how it looks. Y is equal to x plus 1/2 e to the 2x, they didn't put the parentheses in there, plus c. That's how you do it when your function on the right hand side is only a function of x. You don't do that when it's only a function of y. We didn't do anything with those. We just showed qualitatively how they look. When it's only a function of x, just write it in differential form, integrate both sides, you got it knocked. Okay, so let's go back to, any questions on that before we go back to the book?
You explained how you did the u substitution for e to 2x power.
Okay, let me go back to the whiteboard. Okay, you were sounding a little garbled, but okay, here's what I did. If I can get my pen to show up, there it is. Okay, I split this into two integrals. One dx, so that would just be dx, and that's what gave us the x here, plus the integral of e to the 2x dx for that part. Okay, now you didn't have to do a u substitution, but I thought you might find it helpful. The innermost part, the most complicated part of the problem, that would be this part, let that be your u. Let u be the 2x. Then you do a du. Du would be 2 dx. We don't want a 2 dx, we only have a dx here, so divide both sides by 2. Well, this integral just becomes x, and this becomes, now we're dealing with u's, not x's, plus the integral, or let's take this 1/2 du here, take the 1/2 on the outside, and what you're left with is x is dx is du to the 1/2, and oops, yuck, I can't erase here. I was starting to say I can't erase here, but I can't. Let me go back. Okay. The integral of e to the 2x, u is e to the 2x, u is 2x, so this would be the integral of e to the u du. The 1/2 went out front, the e to the 2x became an e to the u. Okay, now this integrates, that is already integrated, and this would, so that'd be x plus 1/2. Now, antiderivative of e to the u is e to the u plus c. Okay, and you just plug back in, plus 1/2 e to the, and u is 2x plus c, and that's your y. Y as a function of x is simply that. You were a little garbled when you were asking your question, so I thought that's what you said. Is that what you wanted? or did you need something else?
Yes.
Okay, good. All right. I know you've had some. Am I sounding as garbled to you as you're sounding to me? I know you can't tell how garbled you sound to me, but am I sounding garbled to you?
No, sir.
Okay, good. All right. I know that was an issue earlier, like a week or two ago, and when I told my wife about it, maybe I told you this already, she said sometimes turning off the video will give you better band accessibility. So it's hard if you have a limited, and we do here, but I have to have the video on because I'm showing the whiteboard. But we have somewhat limited bandwidth here. Now, when we go, my wife's family has a place at the lake. It has terrible internet, no bandwidth. I mean, it's awfully limited there. And then when we go over to the farm in Georgia, again, way out in the country, terrible, terrible bandwidth. So I wouldn't be able to do this from there, okay, either of those places. So anyway, that all you had on this, or did you have any more? Okay, so let's go back to the book. All right, now I've got to move y'all out of the way again. Ryan, you're in the way. Okay, there we go. And here's the definition. That's what we got. Y is equal to x plus 1/2 e to the 2x plus c. All right, now upcoming definition, as well as a method of solution, is just a special case of when a function f in the normal form, dy dx is equal to f of xy. If that f can be factored into some function of x times some function of y, then that is what we say is a separable differential equation. If that f can be factored, strictly x's and strictly y's, and that's what this definition is going to be addressing. A first order differential equation of this form, dy dx is equal to some function of x times a function of y. Not some combination, but some factor. All the x's with one factor, all the y's with the other factor. Then you can say this differential equation is said to be separable or to have separable factors. Okay, now we proceed almost like we did before, just one little exception. So here are a couple of equations. dy dx is equal to y squared x e to the 3x plus 4y. Hey, that doesn't look like it's factorable, does it? Separable? Yes, it is. And let's go to the whiteboard and we'll show why. Okay. And now I've got to move y'all out of the way. James, you're in the way again. Okay. There we go. And I might need to move Kara down just a little bit further. There we go. All right. Let's clear what we got. And let's pick up where they left off. They just threw it out there, but let me show you how they do it. Here is dy dx. There's your derivative in normal form. That's supposed to be an x. I say an x and write a y. And now for some reason, there it goes. My eraser would not pick up. Okay. dy dx is equal to, and there was a complicated looking thing, y squared x e to the 3x plus 4y. That sure doesn't look like it's factorable to me. Unless and until you think about the case, what's the property of exponents? You can rewrite this to be y squared, that's separable. X is separable, okay? But when you got a sum of your exponents, that means it's a product of the things you had. That can be written as e to the 3x times e to the 4y. As long as you have the same base, different exponents, and you're multiplying the bases, you can keep the base, add the exponents. You did that all the time, remember? 7 to the 5th power times 7 to the 3rd power would be 7 to the 3 plus 5 power, 8 power. Well, think of that. 7 to the 5th power is 7 times 7 times 7 times 7 times 7. And 7 to the 3rd power is 7 times 7 times 7. Well, what do you have? You have 8 sevens. Keep the base, add the exponents. Well, now we're doing that in reverse. We're keeping the base and separating the exponents. Now you could write that as y squared e to the 4y, that's some function only of y, times x e to the 3x. Okay. Now, if you're asking me to solve this differential equation, that would be a little bit of a bear to solve. It is solvable, but let's not get into it now. Okay, that's all they wanted you to see. This differential equation, even though these were not factors here, you could write them as factors, and once you did, you could separate them into variables. That was the first one given at the bottom of page 47. Let's look at the second one. The second one says dy dx, written in normal form they call this, is equal to y plus the sine of x. Is there any way in the world you can make that a product of a function of x times y? Any guesses? No way. That's the sum of two functions. You cannot write it. This was the sum of two arguments of an exponential. You could rewrite that to be a product of exponentials. This, no way you can make that as a product of a function of y times a function of x. Won't happen. You can't do it. So the first of those, even though it's really complicated looking, was a separable differential equation. This one, even though it looks pretty simple, not separable. Now, we'll later learn how to solve that one. That's coming up later. All right. So, let's go back to our book. All right. So the first one here was separable. This one, the simpler looking one, was not. And Jermanuel, you're in the way again. Let me move you up here. Okay. So let me scroll down. So this one's separable, this one's non-separable, respectively. The first equation, we can factor that to be, and this is what we did, x e to the 3x, that's your g of x, and y squared e to the 4y, that's your h of y. Now, was that somebody else coming in? 5 people here? Does that work? Yeah, we got 5 here. Perfect attendance, that's right, I remember now. Okay. I always have to check in case someone got bumped out and had trying to get back in. But in the second way, there is no way to make that a product of a function of x times a function of y. Observing that dividing by the function h of y, we can write a separable equation this way, okay? So this is what your separable equation looks like. Now they go to great extents to do this. I think they overdo it, okay? They just introduce so many different things. I'll show you what I think is, okay. James, you're in the way again. Okay, there, I got you. Well, Kara, you're still a little bit in the way. There we go. All right. So let's clear those drawings and start over here. Now, they can really make it seem complicated. They introduce all these new functions. Here's what I say to do. Here's your dy dx. If these are separable, then that's going to be some g of x times some h of y. Now they start doing all sorts of things. Here's what I suggest. Write it in differential form. After a while, I'm going to do it in one step. Write it in differential form. dy is equal to g of x, h of y, dx, written in differential form. Here you have x's together, here you have a y, but you have a y over here. So divide both sides of the equation by h of y. Now we got to assume here h of y cannot be 0. That's going to introduce something on your intervals of definition here. I'm sorry, I said h of x, this is h of y. Okay, divide by h of y here. And these go out, and now you have dy over h of y is equal to g of x dx. Now depending on what the h of y was, if you can integrate, integrate. Here you're integrating with respect to y, here you're integrating with respect to x. This may involve the trig substitution here. It may involve partial fractions here. It may involve, some type of a sine or cosine. Whatever it is, if it's integrable, integrate it. This one, if it's integrable, integrate it. Okay. Now when you do this, you only need to put 1 plus c. Usually we put it on the right at the very end with the x's. It doesn't matter where you put it, but you don't need to put a whole bunch of plus c's. One for the left and one for the right. Just combine them all together and do a plus c. Okay. Now that's how I suggest that you do it. Okay. And if you like their way of explaining it, by all means, they're right on the money, but they just seem like they go around their elbow to get to their ears. Okay, so I've got to move Ryan again. You're in the way again, Ryan. Okay, here we go. So what they do, rather than just divide by h and basically multiply by dx, they first write it like this, divide by h, okay? And then they now call that a new function. P of y is 1 over h of y. Why? Who cares, okay? From that last form, you can see immediately that this will then reduce to a separable function if you just write it in differential form, and you got it. Now, they say, well, what if y is a phi of x, okay? Why introduce all this, okay? It's fine. Then you have the p of y here is a p of phi of x times phi prime. Goodness gracious, can they ever make it complicated seeming? And then they integrate this. This integrates just like we were expecting. This does all sorts of mess here. They're just trying to get it in the form you'll recognize. Well, look, just integrate it. See if it works. So the h of y is equal to some g of x. Now h of y they gave as, and why they chose h, I don't know, but that's the antiderivative of p of y. Why didn't they call it capital P of y? Maybe that meant polynomial. I don't know. But anyway, those are the antiderivatives. Fine, okay? They make it seem so hard. It's not, okay? Now, equation 4, this one right here, indicates a procedure for solving different separable equations. A one-parameter family of solutions, usually given implicitly, is shared by integrating both sides of this. That's what I said to do to begin with. No, there's no need to use, this is what I was saying, to use two constants of integration of a separable equation, because if you do, call it C1 and C2, then subtract C1 from C2 and make that capital C or little c or whatever. Okay, so you only need a single constant. Okay, so let's do example 1. Okay, so let's go back to our whiteboard and do example 1. Now I got to get you out of the way. Ryan, you're in the way again. Okay, there we go. And clear what we got. Okay. I don't know if y'all know what I'm talking about there. I have 4 of you. I don't have all 5 of you. Jesus got bumped off for some reason, but I know you're still here. Because it will only show 4 blocks for you. It shows me, and then Kara and Ryan and James and Jemanuel. Okay, just your names and that you got your phone blocked. Okay, Kara's got a picture. Okay, but whatever. Okay, and that's always somewhere on the screen. And when I'm doing the book, I like to have that at the top because that interferes the least there. Because on the side it blocks off some of what I'm trying to read. You can't see it, so you don't know what I'm talking about, I don't think. But when I'm doing the whiteboard, I want you over on the right side because I've moved the whiteboard as far to the left as I can. So that's what when I say I'm moving y'all around, I'm just having to move your pictures or your names so you're not in the way. So here's example 1. That was way more than you needed, wasn't it? 1 plus x dy. Now this one's already written in differential form. Minus y dx is equal to 0. That's example 1. Now, written in a different way, but still everything's perfectly hunky-dory here. Now, there's several ways you can approach it. I kind of like to get all the y's on one side and all the x's on the other. So I'm going to start with my d's and get those where I want them and then move the other things around. So what I want to do is move this dx to the other side. And since it's a minus here, we'll just add y dx to both sides. That's legal in most states, right? Okay. What does that give us? 1 plus x dy is equal to, because see these add to 0, equal to y dx. Well, I want all my y's together and all my x's together. So what I'm going to do is divide both sides by 1 plus x. Okay. I'll also divide both sides by y. Okay. Now, here the 1 plus x's go out. Here the y's go out. Now, time out just a moment here. Some of you may be panicking and say, wait, you can't go around dividing by things with variables in them because those variables that denominator could be 0. Well, guess what? If 1 plus x were 0, all we've got here is a 0 dy. So all you have is minus dy is equal, minus y dx is equal to 0. Well, that's not very much of a differential equation, okay? Or if y was equal to 0, this side is 0. So then you'd have 1 plus x dy is equal to 0. Well, that's not very interesting either. I mean, you could deal with both of those. But, so we're assuming that 1 plus x and y are not equal to 0. That's why we did it. So what do we have now? We have on the left-hand side, dy over y is equal to the right-hand side, dx over 1 plus. Goodness, this drives me nuts. Okay, well, you got them separated, integrate them separately. Anyone remember what the antiderivative of 1 over y dy is? log absolute value of y. How about this one? Well, you might need a u substitution if you want one, but basically it's just going to be log, natural log of absolute value 1 plus x. And somewhere out here you need a plus c. But you notice since the other two are both logs, this is also a constant, log of c. So I'm going to be real strange about it and do that to you, okay? Now, that may not be important. It isn't in this problem, not where we are now. But what you can do at this point is take an e of both sides if you wanted to. Where is my pen? There it is. Okay. We'll e this, and we'll e the sum of those, but the e of a sum is a product of the e's. Well, let me just do it this way. E of that plus that. Okay. Now, e of log absolute value of y would be absolute value of y. I'm just going to write it y for now. E here, that's the same as e of log absolute value 1 plus x times e of log c. Okay, so this will be a y is equal to, well, e of log c is just c. And e of log x, this is c times, let me clean that out some. Okay. E of this would just be 1 plus x. Okay. There is a one parameter family of solutions. Y is equal to c times 1 plus x. Now, I don't know if that's the form they wrote it in or not. Let's see. Actually, it is. That's exactly how they wound up writing it. Now, I did a little trick there because everything was in terms of logs here, here, and here. I just made the constant a log 2. Log of c is just a constant. Okay? We assume that constant is going to be positive because you can't take the log of a negative number. So just make sure it's a positive constant. Okay. Now, let's go back to the book. I can't find, there it is. I don't know why the pen sometimes disappears on me. Get out of there. Well, that's what I wanted. Okay. Go back to the book here. And now I've got to move James again. He's always in the way. Okay, there we go. All right. So there was our example. Now, hold on just a minute. I have been thirsty all afternoon. For those who were in Cal 3, you remember I just could not get enough to drink. Crammed down lunch without drinking enough, I guess, was part of it. All right. So what we did, they didn't really explain it well. They just said dividing by 1 plus x times y. Well, yeah, that's what we did, but we divided by y to get that separated, and we divided by 1 plus x to get that separated. And you wound up, and they moved it to the other side. They didn't tell you they did, but they did. And that gave you dy over y is equal to dx over 1 plus x. Okay? From which it follows that you can integrate both sides of that equation, and that gives you log y is equal to log of 1 plus x plus some constant c. That's where I put log c because I knew what was coming up. Okay? Now, then you took the antiderivative of both sides, I'm sorry, the inverse function of both sides, which is e of both sides, and that would be e of y, e of log y, is equal to e of log x, log of 1 blah blah blah. Okay, now if you had done this as e of log 1 plus x plus log c, okay, like I did, then you can just immediately take that to be what they did here, and anyway, you get to the same answer. So the absolute value of y is equal to absolute value of x times this log, this e of some number c. Well, that's just a constant itself. Okay. Now, here's the part we kind of fudged on. This was absolute value, that was absolute value. This is 1 plus x anytime x is greater than or equal to -1. Okay? This is minus 1 plus x anytime x is less than -1. That's the nature of the absolute values. Okay? But if you just let that plus or minus e to c 1 be some constant c, you can just incorporate the plus and minus in there, whatever you need for the problem to work. So you can lose the absolute value bars. Okay?
That's what I thought it was, but then I saw that you had just put C and I was a little confused. This is the same problem, right?
Yeah, same problem.
Okay.
Yeah. It's just that they called it C1, I called it E of C. I mean log of C, which is just a constant, okay? My log of C was their C1, okay? And it all works out being the same, okay? Just when everything else is a log, usually it's a good idea to go and make the constant a log 2. Okay, in the solution of that one, because each integral results in a logarithm, a judicious choice of constant, this is what I did, is log of C rather than C. And then rewriting the second line, it would be log of y is equal to log of 1 plus x plus log of c. That's not quite fair to do. Enables us to combine the terms. That was right. That's what we did. Okay. Then when you do e of both sides, e of this and e of the sum of those, that's then e of this times e of that, and that's exactly what we got. Okay. So sometimes it is a good idea, especially if the y is a log function, then it sometimes is beneficial to make the constant a log function as well, because the log of a constant is a constant. We're just dealing with a constant there. Okay. Now in section 1.1 we saw that solution curve may be only a segment of an arc of a graph of the implicit solution. Well, you have to go back to 1.1 and see what they're talking about there. Okay, let's go on and do example 2. How we're doing in time? We got a 3:45. Let's see if we can get this one done. Okay. Now, James, you're in the way again. There we go. Let's clear the screen. And let's do example 2. Solve the initial value problem, if I can get my pen turned right. dy dx is equal to minus x over y. And the initial value is y of 4 is equal to the -3. Okay. Now, let's do what we were talking about before. Okay. Let's get our, first write this as differential form. That would be dy is equal to minus x over y dx. Okay, well, we got our x's together, but this y is out of place, so let's multiply both sides of the equation by y. That gets rid of your y's here, and now you have y dy is equal to minus x dx with these same initial conditions. I won't write them down. So let's integrate both sides. I'll leave the minus sign outside, and this will be antiderivative of y dy, y squared over 2 is equal to minus x squared over 2. Now there's a little part of me that kind of wants to make that constant c squared over 2, but I don't think it's necessary here. I just can't get enough to drink. Of course, I've been talking since 9 o'clock. I had a meeting with the dean, a Zoom meeting with the dean at 9 and other department chairs, and then Cal 2, Cal 3, and now this, so I guess I'm just talking too much. Okay, but let's just call this plus c. There's no reason to do anything fancy with the constant here. Okay? Well, maybe there is. Let's make that c over 2, okay? And then you can multiply everything on both sides by 2, and you have y squared is equal to minus x squared plus c. Or you could write that as x squared plus y squared is equal to, and see, I wanted to do a c squared. I'm going to make it a c squared. C squared. Doesn't matter. I mean, c squared is a constant, 2 is a constant, c squared over 2 is a constant. Do it like that, and there were, hey, what's that an equation for? A circle of radius c, centered at the origin. Okay? Well, all we have to do is plug in our value. We know y is going to be, when x is 4, so we'll have 16 plus y is negative 3, but when you square that, you get 9 is equal to c squared. Okay? So this is going to be 25 is equal to c squared. So c is either plus or minus 5. Okay? Now, does it matter which? I don't really think it does, but if you go back and write your equation down, then it'll be, plug them in here, you get x squared plus y squared is equal to 25. Now, that's your equation. However, that's not a function. Okay? What you want your function to be is y is equal to, remember, plus or minus the square root of 25 minus x squared, but we want it to be the minus the square root of 25 minus x squared. That's where the plus or minus goes. It basically lives there. And we want the minus because when x is 4, you want this to be a minus 3. And that is indeed what you would get. So, in order to illustrate this, I'm going to let the book do the illustration because they've already got it drawn. I don't want to draw it myself. Okay, so let's go back to the book here, and we'll see that they do that work for me. Okay, now let me move Ryan out of the way again. Okay, they did it, they left it just C1, okay, but they ultimately wrote it the way I did. Okay, the solution of the differential equation represents a one parameter family of concentric circles centered at the origin. However, those concentric circles are not functions. Depending on which circle you are and in which quadrant you are, and since you're at y when x is 4, y is 3, that's where you are down here. Okay, so this is the semicircle where that's defined. Now, I didn't put the limits in there. I probably should have. They do, and the reason they do, and this is interesting, notice they put open circles at the end, both ends of that. Why would you put an open circle there? Why wouldn't you put a closed circle? Seems like that would work, wouldn't it? No, it wouldn't, because look at your original problem. dy dx is equal to minus x over y. Y is in the denominator, y can never be 0, and y is 0 there, and y is 0 there. Y can be negative, perfectly fine for it to be negative. In fact, not a bad idea for it to be negative, because then that negates that and you have a positive x. Okay. It doesn't have to be that way, but it happens. So that's why this is your solution curve. Not this one or any part of that one or that one or any part of that one. Your initial condition gets you down to one side, and basically that defines it to be the lower semicircle. And because y can't be 0 and make your differential equation work, you have to have open circles for y equals 0. All right. Does that make sense? Okay. There it is. Had trouble finding my... All right. Now, strange sort of subtopic here. Losing a solution. Be careful, we don't want you to lose any solutions here. Some care should be exercised in separating variables, since the variable divisors could, and this is what I was saying before, could be 0 at some point. Specifically, if r is a 0 of the function h of y, then substituting y is equal to r into that would then makes both sides equal 0. And in other words, r equal y would be a constant solution of the differential equation. But after variables are separated, the left-hand side is generally undefined at r, and therefore we usually exclude it. As a consequence, y equal r might not show up as a family of solutions that are obtained after integrating and simplification. And they call that a singular solution, when there is a value that works but doesn't fit the family of solutions. So example 3 is going to try to investigate that. The problem is, do we have time? I kind of think not. We've got 3 minutes, so I don't think we're going to be able to pull that off. So we'll be starting next time with example 3. So I'm going to erase my marks that I had previously here, and we'll start the next time with example 3. Okay, let me put my piece of paper in place here. And homework exercises in exercise set 2.2 beginning on page 52. Do any of the odds 1 through 21. Then start trying to do some of the odds 23 through 27. And then the next one is going to be based on example 5, so leave that alone for now. we'll pick those up next time. So any of the odds 1 through 21, any of the odds 23 through 27. All right. Any questions? Oh man, I'm not going to let you go 2 minutes early, am I? Oh, that would be terrible. I wouldn't owe you money, would I? Okay. Are there any questions, issues, concerns? Sorry I didn't time it very well. We are getting out early today. Sorry about that. Can you handle it? Okay. All right. If there are no questions, what's that? Okay. I couldn't hear all that if you were talking to me. I'm going to stop the sharing then. And unless there's some question or issue, I'll end the meeting. You okay with that? No questions? Take care of yourselves. I'll see most of you, or some of you, tomorrow. I think it's 3 of you tomorrow. And then the rest of you have a good weekend. All of you have a good weekend, but I'll see 3 of you tomorrow. And we'll meet again next Monday in this class. All right. Take care. Be safe. I think I told you before, the virus is still going around. At least one of my students has it. One of my faculty members in my department, his wife has it and son has it. It's all over the place, folks. Be careful. Be safe. Okay? The guy who has it in my class, he's doing well. He's just has mild symptoms. You know, that's it. However, my faculty member whose wife has it, his son, no symptoms at all. Okay? The mother, she is really, really ill. Okay? I think she's going to pull through and everything, but she is just really sick. You can't tell who's going to wind up with an easy case, if there are any easy cases, and who's going to wind up with really, really sick. So be careful, folks. All right, I used all my time. So unless there's some issue, I will go on and end the meeting. Anything? Take care. See you either tomorrow or Monday, or both, hopefully. Bye-bye.